Good morning. It's 9:15, so let's start. As you may remember, last week we were into tolerant retrieval, and I owe you the end of the lecture. We were in the middle of the Jacquard's coefficient. Before that, I have one question to check that you followed last week. I mentioned that's part of tolerant retrieval, wildcard queries. It's these queries where you have a star in the middle or several stars in the middle. So my question is, which index can be useful to answer a wildcard query? The standard inverted index, the permuterm index, the n-gram index, all of the above, none of the above. Okay, let me show you the results. Oh, interesting. It's actually all of the above. All of the above. Let me explain to you. First, one thing. The standard inverted index is always here. We are not throwing it away. The standard inverted index is where we map the terms to the documents. This is very important. When I introduce the permuterm index and the n-gram index or the k-gram index, this is a complement to the standard inverted index. It doesn't replace the standard inverted index. For example, if you have let's say a very simple wildcard query and I showed you how you can rotate the letters and use the permuterm index, what the permuterm index gives you is only the terms that would match the wildcard, potentially, right? But then you still need to query the standard inverted index to get the document IDs, right? So the standard inverted index is always, in any case, required. The permuterm index allows us to rotate the words. The n-gram index is also one index that can be useful for a wildcard query. It depends. You know, sometimes you want to use the permuterm index, sometimes the n-gram index, but both of them are pretty good for wildcard queries. Right? So often you would not necessarily have the two with you, just pick one of them, right? But both of them are actually good candidates to answer wildcard queries. So the answer is all of the above, because all of the above are actually useful. We need a standard inverted index, and a permuterm index and an n-gram index also are useful. Note that I showed you last time that you can also answer some wildcard queries only with the standard inverted index, but under two conditions. What were they? First, you need a condition on the search structure, because it must support range queries, right? So what do we need as a search structure? Yes? A B tree or a B plus tree, but not a hash table, which is my point, not a hash table. And the second condition that allows us to use only the standard inverted index for a wildcard query is for a very specific kind of wildcard queries, which are? Yes? Exactly, where the star is at the end. Because then it's just a range queries using the B tree in the standard inverted index. So you see that it's not always all the time that you would need the permuterm index or the k-gram index, but both of them can be useful. Thus the answer, all of the above. So let me switch back to where we were last time. I will maybe directly jump to where we were. So I will very quickly fast forward. We were in the middle of spelling correction. There was two things, the wildcards and the spelling correction. The first thing that I showed you for the spelling correction is the edit distance, right? So it's very annoying the way it does that. So I showed you how to compute the edit distance between two words, right? Like cat and 8 in that case, with dynamic programming. So we can compute the edit distance between two words. But the problem is that we needed to compare it, every time we have a query that we want to spell check, we need to compare it to a huge number of terms. This is not feasible. This is just not something we can do. So instead, we have this alternate way of doing things using the k-grams, and surprise, surprise, the k-grams are exactly the same ones as in the wildcard queries. So the k-gram indices and the k-grams are useful both for wildcard queries and for spelling correction. Because here you can see that when two words, potentially you make a mistake here, this is not well written, and this is the one you want to correct it to, you can see that they have a lot of, in that case, 3 grams in common, right? So you may want, instead of the edit distance, to use a different criterion, looking at the intersection of the k-grams, and that gives you a pretty good idea of the distance between two words as well. Yeah, I introduced mistakes last time just to make you think, so that was the missing OMP. And this, for example, if the words have nothing in common, the intersection is very small. So then I explained to you that we can reuse these k-grams indices that we had already introduced, nothing new for the wildcards. And then we have the word that is not well spelled, and then we can look up its n-grams, it's 3 grams in that case, and see that, for example, there's 2 candidates here, computer and Terran, but you can see that Terran is not the right correction because there's only 1 n-gram in common, TER, right? But computer has 5 in common. And then I told you that we have an issue sometimes with false positives. So I just told you be careful about that. It means that you need to be smart about the threshold that you want. Because if you just say the intersection must have in absolute numbers at least 3, then you run into these kind of issues, right? So what you want to estimate is the intersection of the n-grams, but not in absolute numbers. You want to estimate the intersection of the n-grams relatively to the total size here of the union. So in order to do that, we introduce the Jacquard coefficients. I keep saying Jacquard distance, but I should not be saying Jacquard distance because it's actually inverted. So the Jacquard coefficient is 1 if it's exactly the same word, but the distance should be 0. The reason I'm using the word distance in my mind is that the edit distance, the Jacquard coefficients, these are 2 ways of measuring the proximity between 2 words. So it's more for the, let's say, the brain storage part of things. So it's the Jacquard coefficient, and the Jacquard coefficient is very simple to compute. Primary school math, it's the number of 2 grams in that case in the intersection divided by the number of 2 grams in the union, right? This is very easy to do. In that case, it's 3 by 12, 0.25. So this is a relatively low distance in that case. In that case, it's 0.09, even poorer. But in that case, you can see that they have already 0.5. Right? So it's already higher. So you can see that the Jacquard coefficient gives you a pretty good intuition or a pretty good feeling of whether 2 words like computer and computer without O are related. So then what we can do, instead of using the edit distance, which would be very tricky to implement, we look at the k-grams of the query, very easy. We look them up in the k-gram index. That gives us a list of candidates for correction. Then we compute the Jacquard distances. And then we keep the terms with a small Jacquard distance, meaning a high Jacquard coefficient, right? Don't be confused with that. So we still have a resource issue because we would have to extract and compare the k-grams with every single word that there is in the k-gram index. And as you can imagine, the k-gram index can be pretty big, plus when you query for the n-grams for a given search term, you may find a lot of k-grams as well. So you may have a problem at query time. But there is a shortcut. There is actually a trick for this. And you only need the Venn diagram to actually see the trick. It's that you do not actually need to look at all the k-grams every time. Because here we have the query term, and here we have one candidate, but they can of many candidates. and you want to compute this divided by this, right? The number in the intersection divided by the number of the union. So we stopped here last time, so this is the first thing that is new today that we didn't do last time. So first, the k-grams in the query terms, you know them. It's once and for all, it's in the query. So you only need to do it once every time there is a query. So we have a query term here. We know how many, let's call it dash q. We know how many there are here, right? For the one of many candidates that we have, we can pre-compute it in the index. We can store it together with each term in the k-gram index. We can store the number of n grams that it has. And it so happens that we can just use this very simple formula, which is the number of k-grams in the query term, which we know just once for each query, plus the number of of k-grams in the candidate, and this is pre-computed, so you find it in the index, in the k-gram index, minus, and this is the only thing that you need to figure out dynamically, the intersection. So the intersection that would be here, right? And the intersection, it's actually, if I come back when you looked it up on the slides before, where was that? So here, this is the intersection. You can figure it out here, because you can see here that the intersection of the 3 grams between the query here and Terran is just 1, because this is the only one that we have in common, and the intersection with computer is all the ones that are in green. So these you figure out dynamically. And then this here gives you the denominator of the Jacquard coefficients, and this is the numerator. So what that gives you is, we'll directly jump back. This gives you this very simple formula. You divide the number in the intersection by the number of k-grams in the query terms plus the number of k-grams in the candidate term minus the intersection. Okay, who understands this? Okay, it's primary school math, right? But the tricky part to figure out is not so much the mathematical part, which is very easy. It's the idea of knowing that this is computing only once for the query term, and this is pre-computed in the index. So you really have to think of it in terms of efficient computations. Okay? So in that case, for example, if we want the distance between these two, then 5 is the intersection, 7 is the number of k-grams in the query, 8 the one that we found in the index for the candidate term, computer, and 5, again, the intersection, always the same here. And this is what gives us 10, okay? So I've shown you edit distances. I've shown you the Jacquard coefficients with the little primary school math trick in order to make it slightly faster. And finally, if I have to tell you what is actually often done in practice is that you use the k-grams to pre-filter, meaning you use the k-gram index to pre-filter the words, but in the end, common practice is still to compute edit distances, but edit distances only with the few terms that you found with the k-gram index, right? Not over the entire collection. So this is actually how it's done in practice. So you see, we both need the k-grams and the edit distance, okay? Again, I'm not saying this is the one way of doing that. Every time it depends on your use case, it depends on the collection you are indexing, so there is no absolutely right answer, but it's good that you know all of the possibilities to do this. Okay, so that's it for the spelling correction in the classical sense, using edit distance or Jacquard coefficients and k-gram indices. Now there is something very short, also something that's useful knowing. There is more details in the book. When you want to do context-sensitive spelling correction, You may also try all possibilities, like if you look at the words that are in a short edit distance, or maybe using stemming or all kinds of techniques. So you can try to compute all the possibilities, but you see here there is an exponential explosion if you have many possibilities. So the way that you do that is you actually use a lot of bigrams from other users, but on words, not on letters. So if you know that many other people queried for graduate from or from ETH, then you can know that here everything is all right, and all the other ones wouldn't be commonly used. Okay? So what I'm saying here is you can use byword indices in order to also do some filtering. Okay? But I'm not entering any details here, just giving you the big picture. Again, you should read the book. There's a lot of details in the book. It's really part of the exam material. So I really invite you to read the books. Every week there is one chapter of the book. And the last thing that I wanted to talk to you about, which is something completely different, so now you can flush what we've done before, phonetic correction. There is something called the Sandex algorithm, which is another way of correcting spelling mistakes, which using the way the word sounds. And the idea is that every single word can be encoded or shortened to a 4-character fingerprint. What does this remind you of that we've been doing 2 weeks ago? Remember when we looked into how to determine the terms and the equivalence classes over the terms, that we wanted to group some terms together, like window, windows with a big W, and we were building equivalence classes. And then this equivalence class that contains terms, how is it called, this equivalence class? It's called a type, right? And then we can use the types instead of the terms in the standard inverted index. Here, I'm not going to call that a type. That would be an abuse of language, but it's the same idea. You could actually use these 4-character fingerprints in order to do equivalence classes between words, and then index. Instead of indexing the words, you are basically indexing how they sound. But let me show how this is done. This is very clever. The idea, so let's say we have a couple of words that we want to encode. You can see that the first two, they kind of sound the same. Computer, computer. So you would like, ideally, for the Sandex algorithm to find some similar fingerprints. So here's the idea. We have the letters of the alphabet in here, and they are grouped in 7 packets. You can recognize that the vowels are all in packet 0, and then we have R on its own, M and N, the nasal consonants, L, D and T, the dental consonants. We have the buffer, so the labial consonants. So you see they are all grouped into meaningful groups. So now what we do is that first we replace each letter with its code from the table, except the first one. The first one we don't replace, we keep it. Right? We keep the first letter, and then we replace each one. So E is 0, T is 3, and so on and so on. So we replace with the codes. Okay? Then what we do here is we eliminate repetitions. So you can see here we have 3, 3 because of the double T, and we replace it with a single 3, which makes sense because letter, you know, double T or T still sounds the same. So we remove duplicates. The next step is we remove the zeros, because actually we want to keep the fingerprints of the consonants in this algorithm. And the last part is, you can guess it. I told you it's a 4-character fingerprint. There you go. You just cut or pad. So you take the first 4 here and you cut. So you cut right here. Right? But this one has 1 not enough, so you add a 0. And surprise, surprise, you can see that here, computer and computer, they have the same fingerprints, right? So this is called the Sandex algorithm. Who think they understood the Sandex algorithm? Okay, so you could do it on some words. Okay, so let's see. Here, I have a Sandex. What is the Sandex representation of paper? And I can show you again the slides. Okay, I hope I checked the right one. Yes, exactly. So how did you do it? It's very easy. You replace, so the P, you keep it. You don't replace the first letter. Then A is 0, it's a vowel. Then P is a 1. Then we have E, it's a vowel, it's 0 again, and R was 6. Then there's no repetition here, but so we can remove the zeros now, here. And then the last step is we need to add it to 4 characters, okay? So this is the correct answer, okay? Very good. And the 116, the trick was just that the first P is actually not replaced by a number, because it's the first letter. And even if it had been, no, yes, it could have still been 0, 1, because there would have been the 0, the A, the 0 in the middle. So the only reason why P116 is not the right answer is because the first P is not converted to a number. The second one is not the correct answer also for the same reason. We need the first letter, and the first one also. Okay, so this is the Sandex. So now, I am going to, this is the end of that one, I think. Oh, I had, on the last slide that I added, I actually had one more question to reactivate the Jacquard coefficient. So if you take these words computer and computer without the O, using 2 grams, in the slides we use 3 grams, but now we use 2 grams, what is the Jacquard coefficient between these two words? And you see that here I'm activating your medium-term memory, because I talked to you about the Sandex coefficients in the middle. So we'll see if it's still activated. So there's no secret. You may need to just write it down. By the way, who already saw the Jacquard coefficient in the machine learning lecture, Introduction to Machine Learning? You already saw it, okay. It's the same thing. The Jacquard coefficient is also used in when you compute similarity between, for example, images. It's the exact same definition. Okay, so you still need time? Okay, let me show it. Yes? You still need time? Okay. Oh, okay, interesting. So, you know, I'm never excluding the possibility that I may be proven wrong. But let me actually show you the slides. It's the idea. So I added this. So these are the 2 grams of the word computer. So you see $C, COOM, MP, PU, UT, TE, ER, $. And then computer, it's $C, CM. Sorry, the dollar should not be here, just CM. MP, PU, UT, TE, ER, and $. How many are there in the intersection? 7. Here we have in total 10, so it's 7 divided by 10, 0.7, okay? The trick here, and I actually told you about that, we are using the dollar at the beginning and at the end, right, in the k-grams. The idea is that we want to catch, for example, for wildcard queries, when we have, you know, a star at the end, at the start, and so on and so on. So we want to know when the word ends. So this 2 gram here encodes the fact that R is the last letter of the word, and it is very important, just as important as the other. this one encodes the fact that they both begin with C. So this is why we need to have this information as well, right? So this is the trick. And those who found other numbers may have forgotten. Who forgot about the dollar? Some of you, right? So here, this is why we have 7 divided by 10. Okay. So these are, who understood the k-grams? Who understood the k-gram index? The k-gram index is just an index. It's a B tree where you index the k-grams, and then you have the list of words that they all have. It's very similar to the standard inverted index, except that in the standard inverted index, you index the terms, and it's the documents that are then listed as postings. Okay? So let's now move to the next part of the lecture. But don't worry, I will start with a recap, as I always do. So now we are done with tolerant retrieval. So the next part of the query, it's in order to scale it up. How do we construct the indices? So far, we had the standard inverted index. The standard inverted index, as we saw, is made of terms or of types, if you use the equivalence classes with lemmatizations and so on. So we have here the terms or the types. I will just say term to keep it simple. And then we have here the document IDs. It's the documents that are associated with every term here. And this is here the frequency. So we have the number of, every time the number of documents that are right here. So this is the standard inverted index. Note that the permuterm index and the k-gram indices are actually not so different from here in the sense that in the permuterm index here we have the rotations, and for the rotation we have just, it points to the word that is rotated. In the k-gram index we would have here, instead of the terms, we would have the 3 grams or the 2 grams, and here we would have the list of the words that contain the k-gram, right? But the idea is always the same. So I told you about search structures. Why do we need the search structures? It's just that here we need to be able to search here. It's not enough to just have the list of terms. We need to find them. How do we find them? We have 2 ways, hash tables and trees, B trees, B plus trees. Okay? We have tolerant retrieval, which I introduced you last time. We started with Boolean retrieval, with exactly the terms that we wanted, and Boolean operations, and, or, not. And then we said, okay, what if we have wildcards? And then I showed you with some more indices, you can also answer these queries. And what if we do mistakes with spelling corrections? Well, we can do that as well. And we also have special indices for that. So we saw these 2 new indices, the permuterm index and the k-gram index. This is what we've even seen just recently today. And again, I want to say again, the overall structure of the permuterm index and of the k-gram indices, 2 gram, 3 gram, are very similar to the inverted index, except that here we associate the rotations with 1 word every time. And here we associate each k-gram with the list of the terms that contain the k-gram. Okay? And they also have a search structure. You would also have a hash or a B tree in order to, or a B plus tree in order to search through that. Okay? Who sees the relationship between the standard inverted index, the permuterm index, and the k-gram index? Not all of you? Who doesn't? Who doesn't know if they know? Okay. I will maybe come back on that a little bit every week to make it clear. The idea is that every time you have an index that looks like that, with the terms associated to the documents, or the rotations associated with the terms in the permuterm index, or the k-grams associated with the terms in the k-gram index, right? But the idea is always the same. And again, I cannot emphasize enough that to compute these queries, we always need the standard inverted index. We don't throw it away, because otherwise we don't know the documents, right? So we do a first search with the permuterm index or the k-gram index, and then when we have the terms, we can look up the standard inverted index. Okay? So we looked into the edit distance as well. that compute the number of edits. So here it's removing C, replacing T with R, adding the E, and so on. You know how to do it, dynamic programming. We looked at the Jacquard coefficient, which you did again. It's general, by the way. It's not just for k-grams. You can do that with any two sets. If you have two sets, you can compute the Jacquard coefficients. The k-grams are one way of building the sets. And we looked into the soundex encoding, which is one way of building equivalence classes between terms by the way they sound. OK. So I have one more question, because I like to test how you are following. About the search structures, we looked into B trees and B plus trees. So I'm giving you a few data structures, 4 of them, and I'm asking you which ones are 3, 5 B plus trees. This is the third one. The fourth one. Who needs more time? Please raise your hands. Okay, let me close it. So let's see. Oh, very interesting. So it was actually useful to ask. So this one is a B plus tree, a 3, 5 B plus tree. So now let me take the easiest. Why is that not a 3, 5 B plus tree? This one. Yes? Exactly. So what is it called? A B tree. B plus tree means we only have the keys of the index at the end. So this is a B tree. This is not a B plus tree. Next, why is this one not a B plus tree? Anybody? Because in a B plus tree, the leaves must all be at the same depth. We cannot have these kind of things. We cannot have here at depth 1 and some others at depth 2, right? It needs to be everything at the same depth. Okay? So this is why that is not a B plus tree. Which other one do we have? Why is this one not a B plus tree? A 3, so it is a B plus tree, but it is not a 3, 5 B plus tree. So why is it not a 3, 5 B plus tree? Yes?
We have too much entries in the first two leaves.
Yes, but they have less than 5.
Yes. Yeah, well, we have then 6. We would have 6 per children if we would have attachment.
Yes, exactly.
Children and not
Exactly. So it's this trick that I told you about the intervals. We basically say if we have a 3, 5 B plus tree, this is the interval for the number of children. So we can have between 3 and 5 children. So here we have 5. Note that for the roots, it's okay if it has less. But here we have 5 children. But this actually condition is equivalent to saying it's equivalent, children, it's equivalent to saying that we have between 2 and 4 keys on every node. This is equivalent, right? And this condition, equivalent to that one of between 2 and 4 keys, it also applies to the leaves, even though they do not have any children, right? So this is why here, virtually, we would have, as you said, 6 children here and here. So this is not a 3, 5 B plus tree, because we have too many keys. It should be between 2 and 4 keys everywhere. Why is this one a 3, 5 B plus tree? The root has 2 children. Yes. Exactly. Yes. So you cannot have more, but you can have less. And as I said, do not push it to the root having only 1 children, because that's totally useless. I mean, you can add as many roots as you want with 1 child. It's just useless. So typically, the roots can have 2 children, 3 children, up to 5. So 2 children is OK. Perfect. So you nailed it. This is a 3, 5 B plus tree. And you can look again at the slides that we had the last time if you want more details. And again, B trees, B plus tree, this is a bit tricky sometimes because you sometimes have different conventions. And I tried to be as generic as I could last time to give you the general principles. And in particular, I told you there's two ways of computing these intervals. The intervals must always be more or less simple double. So A to A, D to D, and so on, roughly. But the way it's done is that some people say it's D to D plus 1. Some other people say it's D to D. So this is why you can have 3, 5, but you will also find people that say 3, 6. Okay? Both are fine, right? Perfect. So who understands B plus trees? Awesome. So I have actually one word to say about that. We thought of having you implement B plus trees, but we are extremely careful about having a reasonable workload that we put on you every week. It turns out that the week, I think it was the last time where we asked byword indices, positional indices, that was a lot. And we are aware of that, we heard you about that, and the TAs made a poll. So we are going to be careful not to push the workload too much. This is a 4 credit point lecture. The B plus trees would actually have, yes?
I have a suggestion that for the grading, if you look at it, that you actually say this task will be looked at, and the rest you will upload for us to practice, but only for us. So that if we want to go for the 0.05 grade, then we know which task to do, and we know which task we can do in the holidays if we have time.
So you heard, right? So
I'm sure that aligns with what we want to happen during the session. So we think about it next session. So I'm not sure that we can do that.
what I can add is one thing maybe to make you feel better. It's called grading, but it's not actually grading. It's either or. It's either you did it or you didn't do it. So what we want to see is just that you actually made the effort of doing the exercise. So it's really just check, not check. There is no intermediate grade or anything. Yes?
Yeah, but I don't know what to expect if I only solve one of those tasks. And if I solve it, if I take a long time to solve it, and I don't have time for the other tasks, and the TAs look at it, and I don't know if they count as a reasonable effort or not.
Okay, yeah. So that is third. So maybe you can communicate more on the criteria. So there's two things in there. There is first that we will communicate on the criteria. The TAs will communicate on the criteria. The other one is that anyway, we are well aware that the workload last week was a lot, right? So we are reducing it, yes?
All in all, I'm not against a lot of exercises. I'm just against doing them on time. Because if I have time in the holidays, I will spend my time to do these exercises to get the concept.
Uh-huh.
But now I'm quite a bit stressed. So.
Yeah. Okay, that is very useful to know. And I encourage you to give us this kind of feedback. So this idea with the extra bonus points, this is it's still an experimental kind of semester. So next semester in fall, there will be the official start of the Learn Elementa, so the ETH guideline for that. This semester, we are trying it out. So this kind of feedback is extremely valuable to us. So do not hesitate to tell us that, to send us also feedback via email. I think you can do it anonymously on Piazza. As well, do not hesitate to give us that kind of feedback because it can also be useful. We talk to each other between the lectures. It's very valuable to have this kind of feedback, right? So we will be more specific on what to expect of what we call reasonable, let's say, right? Okay, so thanks a lot for this. So what I was saying regarding the B trees is a B plus tree is very hard to implement. So it would be maybe pushing the workloads. So instead of that, we are going to make you work on the K-gram indices, right? On implementing K-gram indices and towards tolerant retrieval. And we are going to just do one programming assignment. So the reason for the workloads the week before was there was two programming assignments. There was the byword and the positional index. And from now, we are going to have just one programming assignment every week, okay? So do not hesitate to give us feedback. This is really very important to us. We want you to learn. We want you to do good at the exam, to be prepared for the exam. We want you to learn what we are teaching you. And all of this is to support you. We are doing this to support you in your learning. So let me get back to nothing. It's actually 10 a.m. So let's take a break, and then I will continue on the index construction at 15 past 10. Okay, so let's take it from there. Let's go to the second part of today's lecture, starting on index construction. So we've seen a lot in terms of the querying model. We look at the Boolean querying model, and we've seen a lot of indices and constructions. We have implemented some, but it was more or less in memory. You read from the disk, you do it in memory. The problem is that sometimes it can be so big that you need to actually learn how or understand how hardware works. So you all know it's the basics of any computer system. So we have the CPU that takes care of the computations, but it also has the registers and stores a few things in there, like the cache. We have the memory, which is the RAM that mostly the CPU interacts with. We have, oh, that's, indeed, you don't see the slides. The recording, it's on the recording actually. So we have the CPU, we have the memory that I commented on, and we have the disk, which is the durable storage. And finally, the network. If you start having clusters of machines, you also want them to communicate with each other, or if you are indexing the web. So I have this quick question on, I think it should be easy, right? You're computer scientists, so it's almost the 101. But it's just to, let's say, load that back into your mind for the duration of this part of the lecture. So what is the slowest to the fastest? And I'm thinking here of latency, meaning the time that it gets for you to start getting the information. Meaning I don't mean the throughput, I mean the latency. Okay, let me make it short. So yes, you got it all right. So this is perfect. So we have this whole hierarchy of storage with the RAM, the CPU cache, the disk, the tapes, and so on, with the idea that this is slower, this is faster, and here you are closer and closer to the processing part of things, right? The first two are volatile, meaning you shut down the electricity, it's gone. Here, it's actually durable because you shut down the electricity, you keep it. What it means is very simple. It means that the indices that we build, we have to have them on disk, not just in memory, because we don't want to lose them. So we need to have the standard inverted index, permuterm index, and so on, stored on disk, which doesn't mean that we don't load them in memory for actually processing the queries. The latency, this was the sense of the question. This is very slow to read, and this is very fast to read. Maybe you thought that this is gone and no longer used, but actually it is. And I think even ETH still has that. I think your data at ETH is still backed up on tapes somewhere because it's super cheap, and it's in some remote place where the robots get the tapes if you want to read, but the latency here is extremely high just because you need to wait for a couple of hours or days until they actually find the tape and so on. But anyway, and the fastest is when you have everything next to the CPU right here. But we are going to focus on the memory and the RAM a lot today. The costs are also important because if memory was cheap and the CPU cache was cheap, then we would just use them, right? It matters also that we have costs and we cannot have the memory arbitrarily large. So this is something I'm just reminding you of because we saw it in the introduction. The capacity the throughput, how fast can we transmit the data, and the latency when you start receiving the data. And I showed you that we had this issue with the progress that was made, that we have a lot of capacity, less throughput, and less latency. And this is relevant for big data, but as it turns out, we are almost in big data if we have a lot of documents to index. So this matters actually a lot to us. So if you look in terms of capacity, typically you have a few megabytes here. You have gigabytes up to 4 terabytes. I look at it every year to see the current settings. You can have 4 terabytes of RAM on some very expensive machines. You can have 12 terabyte hard drives that exists. And you can even have petabyte range here, maybe not a single tape, but in the actual storage center. So this is to give you the order of magnitude, and this is important if you actually try to build your indices. Then there is the latency, which is nanoseconds here, tens of hundreds of nanoseconds for the RAM, milliseconds for the drive. So you see the order of magnitude is very different. That makes a big difference. And here, but we are not looking too much in there, can be hours. The throughput is ultra fast here, 1 terabyte per second. The order of magnitude here, 10 gigabytes per second, 500 megabytes per second. So we see it's slower and slower in terms of transfer. Here it actually, it's even slower. I should have pushed the arrow here. So this gives you the impression, capacity, latency, throughput, just the orders of magnitudes. Why do we have latency on the disk? It's actually because of the way, if you use a magnetic disk, it's less the case with SSDs, but there is actually a part that rotates here, and you need every time the time for the heads to reach where you are reading, plus this needs to rotate and be on the right location. So this is what we call a seek. And the problem is that if you try to fetch just 1 byte of data on the disk, or let's say one single posting, one single term, you are going to wait a lot for the seek when nothing happens, and then you transfer that 1 byte that you were actually attempting to read. This is ridiculous. You're basically waiting, and then you barely use the transfer here. So what do you have on hard drives to solve that? You all know that. Do we read single bytes from hard drives? Yes?
No, we read blocks or lines.
Exactly. We have blocks. So typically the order of magnitude is kilobytes, so 64 kilobytes, let's say, depending on the file system. And when you have a block, then suddenly you can see latency is no longer the issue because you load the entire block. So now the bottleneck is more in the transfer than in the latency, which is much better. So this is why the lesson learned here is we love reading blocks from the disk. And this is what we need to keep in mind now that we want to design the index construction. We have to find a way of building the index that is block friendly on the disk. So we want to send to and from memory in blocks. That's the one thing. The second thing is we like to cache in memory. Because since this is very slow, we would like to have more things be done here between the CPU and the RAM than is actually done between the RAM and the hard drive. It's also because of the efficiency for the transfer rates and so on and so on. So what is actually happening when we cache things is that we load it from the disk and then it's in memory and we directly read it from memory for a while, and from time to time we may need to put it back on disk if we modified it and read it back, or maybe cache something different from the disk depending on what we need. So this is caching. This is the second thing. We want to read in blocks. We want to cache things in memory and work actually in memory. And there's even terminology for that. So we read a block. It's put in a buffer in memory. And there is one more thing that I haven't yet spoken of, which is that sometimes we have idle time because when we actually load something from the disk into memory, the CPU may do nothing because you're just waiting for it to happen, and then you start working, and then you're idle again until the disk is read, and so on. This is a waste of CPU. And when you deal with data databases or even in general data flows, it's also for machine learning, for anything, you have the CPU, you have the memory, you have the disk, and you have the network. And very often, one of them is the issue. Like the network is used at its maximum, and the CPU is underused, the disk is underused, or maybe in a different setting, the CPU is going 100%, but you are barely reading from the disk. The ideal setting that we would all wish for would be that everything is used 100%. The CPU is used 100%, the disk I/O is used at its maximum capacity, and the network as well. In practice, it never happens, but you try to make it work in such a way that you avoid these inefficiencies. So what is the trick here? And this is something we will see after the vacation. It is that since the CPU is idle, we can actually compress some of the stuff here to save some space and save some time in the transfer rate, and use the CPU to do the compression and decompression, right? This is a way of fixing that. So here it's like a preview of what we will do after the vacation. So we can use for compression and decompression. Speaking of compression, here's still a first one that we can do today, because this is going to be useful. Plus, it's going to be a great refresher on the terminology, term, document, type, token, and so on and so on. So the term IDs. You knew about document IDs, but I never told you about term IDs, right? The document IDs, these are just numbers or some kind of IDs that identify the documents. Document 1, document 2, document 3, these are document IDs. But we never use term IDs. Actually, if we have an index here, we have the IDs here of the document, but we don't use IDs for terms. We just use the terms or the types if we use equivalence classes. So we don't use terms. Here we have posting lists. The posting, is this a term, a document, or a token? Who thinks it's a document? Who thinks it's a token? Yes, it's a token. Why is it a token? Because actually when you see, for example, 4 here, it's not actually 4 alone. It is the pair CPU 4, because its location matters. This 4 here is different from the 4 here. It's the same document, of course, but here it's CPU 4, here it's information 4, right? This is a posting or a token. It's the same thing. So actually, this is how it's stored in memory. We just store the document IDs, but this is already an optimization. This is an optimization of this, because what we actually have on the logical level is that the term retrieval has these tokens. It has the token retrieval in document 3, it has a token retrieval in document 5, and it has a token retrieval in document 7, right? This is a token, right? This is not the same thing as the document alone or the term. Who understands now what a token is? Okay, it's a pair of term documents. Okay? But of course, this is highly inefficient. It's highly inefficient, but we still need to think on that level. Because now, what happens if I go back in time? Here we have the index, it's built. Now I go back in time before it's built. If I rewind a bit, before we actually sorted them all and nicely organized them by term, all these tokens, it was all a mess. I mean, it's just all these tokens, pairs of term documents, everything that we found. And if I rewind even more, they were even grouped by documents, not by term. They were grouped by documents because they appeared in documents. Here we have document 1 that contains ETH computer data information. Here we have document 3, document 2, document 4, document 7, and document 5. So of course, we lost information here. We lost the order, and we lost the number of occurrences, right? Which is fine. So if I rewind even a bit more, I actually have the original documents. So the whole point of building the standard inverted index is to extract the tokens from the documents, group them by terms rather than by documents, and then build the posting lists, right? So if we actually need to manipulate this in memory in order to build the index, you can see that it takes a lot of space, because here we save space, but here not. Here we have actually stored the bytes of the terms. We have a lot of replication, and this is where we can compress a bit. So here's an example this is actually an example that is used throughout the book as an example of data sets, and we will use it again for data compression. It's the Reuters RCD1 collection, which is 1 gigabyte of text, 100,000 documents, and 100 million of tokens. Today, it would be considered quite small. I mean, we can do that probably on a single machine, but we can still learn a lot from what is in there because it gives us some orders of magnitudes in the relationship between terms, documents, tokens, and so on and so on. So let's do a bit of math and look at it closer. So we have, let's say that we have the term, it's stored in bytes, and let's take 10 bytes in average. I think the average is 8.5, if I correctly remember, 8.5 bytes per term, but let's take 10 bytes in average. Here we need, let's say, 32-bit integers, so let's say 4 bytes. Of course, if you have more than 4 billion documents, that's not enough, but you need to adapt this to your system. And if you multiply that 14 bytes by 100 million tokens, that's 1.4 gigabytes in memory. So if we have we extrapolate now. If we have 16 gigabytes of memory, meaning it's your laptop right here, you don't have this expensive 4 terabyte of RAM computer in the cloud, but just your laptop, we would fit in there 1.1 billion tokens, which is 11 gigabytes of text. It's not that big, right? But we would like to process maybe bigger collections than just 11 gigabytes, right? The internet is actually much bigger. So what could we do? And I actually already gave you the answer in the title of the section. We can. What can we do? Yes? I cannot hear you very well. Mm-hmm. So you mean we can use term IDs instead of the terms, right? We can encode that way. Yeah. So let's encode the like this. This is the trick. Instead of actually storing every time ETH Zurich computer and so on, we replace it with some ID, which is called the term ID. We have T1, T2, T3, and of course we need to keep somewhere the mapping to not lose information, right? But this takes actually less space. This is the actual mapping. It should go both ways. I think you have both uses. So here we are mapping T1 through T7 to some terms, but this we only store once in the term to term ID mapping, right? So it means that now we should use less space because now it's 4 bytes and always 4 bytes. It's not even a variable length. So here we have 8 bytes, still the same number of tokens, so it's 0.8 gigabytes. So of course it's not great, but we still gained a bit of space. We can now process 2 billion tokens and 20 gigabytes of text, okay? So it means, you see that we have kind of a bottleneck here because we can barely process slightly a bit more than the memory that we have. But typically we could have documents on the terabyte or even bigger range, right? So I would like to show you how we can do better than that. Better than just replacing terms with term IDs, we can even push the limits to process even more text, even though we only have 16 gigabytes of RAM. And the idea is very simple. If the RAM, if the working memory limits us in the number of documents and tokens that we can process, then let's use the disk, because we have a disk as well, right? And that disk fits 12 terabytes, potentially, if you take a very large disk. That's 5.3 terabytes of text. That's much better, right? But now the problem is, if we actually use the disk, instead of the memory in order to index this many terabytes of text, of documents, this is going to be extremely slow because we are constantly reading and writing to the disk. This is not practicable. This takes too much time. So we need to find a way that we do use the disk as storage, but we try to be very parsimonious in the number of requests that we actually send to and from the disk. This is called batch processing. Batch processing is exactly the way to circumvent the discrepancy between latency and throughput. Whenever latency starts to be a problem, you batch process, meaning you start reading into blocks. So this is what we are going to do here in our first attempt. We are going to try to write and read blocks from the disk and do the work actually in memory. Okay? So first, here's an idea. It actually comes from the big data universe, this idea here. It's not something specific to information retrieval. It's the idea of sharding the document collection. So if you have, let's say, 1 billion documents, you can make it maybe 100 shards, and each shard will have 10 million documents, right? So that's the first thing you do is shard the collection of documents into smaller units. In that case, just 3 for the sake of explaining it. And the idea is that you first start with this one, the first shard, and then you take the second one, and then you take the third one. But every time you only look at that one shard that we have here, so it fits in memory. And you see that because of the number of shards, we can actually make it on larger quantities. Because we are only using the memory, we can contain 1 shard at a time in memory. Who understands that? Okay, so now we will go ahead and actually come up with a way of making it work, which is the idea that every time you take a batch of documents, you do stuff, you compute the index or the partial index on it, and you write it back. So maybe you computed some standard inverted index, but only on that batch of documents, you write it back to disk. Then you take the second one, and you write it back to disk as well. And then the third one, and you write it back on disk. And every time you could use efficiently all the RAM that you had, 1 shard at a time. And the idea now that you have all of these intermediate standard inverted indices, you need to merge them back, because in the end you want 1 single standard inverted index. So the idea is that you take them all, merge them into memory, into the final index, and then you write the final index back to disk. And then you're done. So you see that this idea drastically changes the amounts of tokens and of documents that you can process, right? And it really can be a factor of 10, 100, you know, as large as the disk allows, but much more than what the memory allows. Who understands this general idea? Very good. So now I'm just zooming in. I'm actually showing you more details on what happens. So now I'm looking at when we process the batches one by one. So when we process the batches one by one, we have these documents on this. So we parse them. We read the pairs. Here I need to take care of the term mapping as well, because I want to keep track of the term IDs, right? So what I want to generate is term ID, doc ID pairs into memory, right? So I need this term to term ID mapping that I have somewhere. So you see that, just so you see, I use colors here, but you can see that the term IDs here, I use these very short blocks here. For the terms, I use the variable length blocks here to make it clear that this is the terms that is very inefficient, and this is the compressed terms. These are the term IDs, okay? So what you have in the end is, once you have parsed these documents and forgotten about the order and the number of occurrences, what you are left with is a huge set of term ID, doc ID pairs, the tokens, okay? What is the way you generate these term IDs? Because it doesn't happen magically, you have 2 ways. The first way is you do a first pass through the documents only for the sake of the term IDs. You look at every single term that you find into all documents. Maybe you lemmatize, maybe you use some equivalence classes, but you try to find all the terms, and then you assign IDs, and there you go, you have your mapping between term and term ID, and the second pass you can use in order to build the index. Okay, that's the first way. The other way, if you actually don't like to have 2 passes, you can just do it on the fly. Whenever from a document you get this token, but with the actual complete term, and it's the first time that you saw it, then you update dynamically the mapping between term and term ID, plus you transform it into a term ID, doc ID token. Okay? So either you do a first pass, or you do it on the fly. So now this is solved. We have the term-to-term ID mapping. We have the tokens, term ID, doc ID. What is the next step? What do we do now? We're building a standard inverted index, right? So what do we do? Yes? We create the posting. What do we do with that? It's all messed up here. It's all in some random order. So how do we build the posting lists out of that, the standard inverted index? We need to group them, sort them, and group them by term IDs, right? So we need to sort. We need to sort them, and then once it's sorted, we can group by term ID, okay? And then we merge back to the posting lists. Oh, there is an overlap here between this and this, but this is just the mapping from the term IDs to the lists of postings right here. And you see what happened here, it's extremely important. We only have the document IDs here, but it's only for space efficiency because the term that is part of the token as well, the term is actually stored on the left of the standard inverted index, right? But logically what we have here is tokens, even though we only store the document ID. So now we have these posting lists, we get them back on disk. Here you can see what it looks like. We write back the standard inverted index or the posting list just for that one batch of documents to disk. So this is how it works. We zoomed in on one single batch. Now that we have that, it's the disk here still. We have several inverted indices for several batches of documents. We need to merge them. But in order to merge them, we have the problem that this doesn't fit necessarily in memory. Sometimes it's much bigger than memory. So we need to figure a way to actually merge them from the disk to the disk, right? How do we do that efficiently? Okay, let me tell you. So we actually have pointers there. I open some file or file descriptor here, here, and here on every posting list, and I'm basically keeping the pointers, and I'm going to write in one single write the entire final result. So I will need a bit of memory, of course, but first I start with the yellow term ID, and then I'm using this everything that I load from here plus here, so I load it all in memory. I may need to merge the document IDs because the document IDs must be sorted, right? So I merge them, and then I write back to disk. Then I do the same thing with the reds. So now I have all three posting lists here. I put them in memory, I merge them, and then I write it back to the disk. Okay? And then I just continue, and you can see that it works because we only need to go forward. We don't need really random access here. We really keep reading the files linearly. So this is why it's extremely efficient. We just have pointers that go through the index files and just merge as we go, the purple one and the brown one. And there we go, and we are done. You should see the similarity here with the intersection of postings, right, that we've already been seeing. It's exactly the same idea that you concurrently scan all the inputs in parallel while sequentially writing the output. Who understood what went on here? Okay, very good. So this is called blocked sort-based indexing. What do you think the complexity of that is? So I mean with complexity, building it, and I give you T as the number of tokens, like a billion or something. So the way I did it here is a bit like the weather forecast. You know, when Meteo Suisse or in other countries, they give you the forecast temperature, they don't only tell you what's the actual temperature, they will also tell you how it feels. So sometimes you may have -5 degrees, but it actually feels like -10 degrees, right? And here it's a little bit the same, that we may have some complexity in here, but it may feel differently because of the constants, because you may have a constant that is bigger or smaller, and then it may change the way it feels. even something exponential can feel like O of 1 if the constant is ridiculously small, right? So this is why I'm telling you this. Okay. BSBI is blocked sort-based indexing. It's just the abbreviation of this. It's the whole idea of sharding and building the standard inverted indices in memory while sorting and then merging on the disk, BSBI. So let's see. Very good. Who answered to this without looking at the slides? Some of you, very good. Okay. So indeed, T log T. Why T log T? Because of what? What is the typical algorithm that executes in n log n? The sorting, exactly. So T log T is because of the sorting. Every time we sort, and so the constant is because of the number of batches, right? But the complexity is with respect to T is the same. So it's T log T. So that's the first step. It's the generation of the standard inverted indices. It involves sorting, so it's T log T. The second step is O of T, and it's O of T simply because, as I told you, all we are doing is scanning through the input and output. It's linear, right? Who understands that it's linear? Very good. So in the end, it's O of T log T because T log T wins. But in practice, it feels like O of T for a very simple reason, is that this involves accessing the disk a lot, and this is extremely slow. So here we have an enormous, compared to here, we have an enormous constant. And here we have a smaller constant. So if you have something linear with a very big constant and something in n log n with a smaller constant, in practice, what dominates is O of T. So it still feels like it's linear in practice. But the theory, a theoretical computer scientist would jump and tell you, no, that's T log T because that's the theoretical complexity. So that was one way of doing it. So I told you replacing terms with the term IDs buys us some memory. Blocked sort-based indexing, we shard the document collection and process it one shard at a time, merge at the end. That's called blocked sort-based indexing. We can do even better. There's another technique that is commonly used, which is called single-pass in-memory indexing. So this one, people call it SPIME. I always get confused with all these terminal, with the abbreviations, like replacing it with abbreviations. So that's why I spelled it completely here, like single-pass in-memory indexing. So processing a block is the idea of BSBI here. The way we process the blocks, as I told you, is we extract the tokens into term ID, document ID pairs, and then we sort them. This is maybe not the most efficient way of doing that because we need the extra sorts. Why wouldn't we, instead of sorting the term IDs, doc IDs, and at the end sorting them and generating the standard inverted index, why wouldn't we directly generate and maintain a standard inverted index with the terms directly? Why? Because suddenly we're no longer in n log n, we are in n. Here we don't need to sort anymore. Imagine that you use a hash here. It's very efficient. Plus, the other aspect of that is if you use the terms here, you no longer need the term-to-term ID mapping. And the term-to-term ID mapping, it can take some space in memory. If you drop the term-to-term ID mapping, then you don't need to remember anything between the passes. You have nothing in memory that is used for anything else than processing the current shard. So here, we just keep maintaining the standard inverted index and build it, but it takes less time because we don't need to actually sort, we just maintain it. Okay? So this is SPIMI. Okay? So the construction in memory is slightly different. Again, we use the terms, not the terms IDs. No need for the dictionary of term-to-term IDs. And we maintain the structure on the fly. And then at the end, of course, we need to sort. Especially if we had a hash, if you used a hash table to do that, you need to sort the terms here. we will see why you need to sort the terms by, like, let's say, alphabetically or lexicographically, and then you store on disk. And the really important thing here is you do not need to store the term-to-term ID mapping anywhere in memory, so you do not run the risk that the more shards you have, the more you need to waste memory kind of for this, because then you start having less and less space for doing the actual standard inverted index building. So this is a huge gain in terms of scalability, because suddenly we can process as many shards as we want. We have no states to maintain, right? Who understands this? That it scales up better? Okay, awesome. And the final merge is actually very easy. It's just that we don't use the term IDs, we use the terms, but because it is sorted, we can do exactly the same thing. Again, the sorting, the fact that it's sorted is very important. It's because it is sorted that we can open the pointers and just scan through the input and scan through the output, which gives us the O of t at the end. Oh, I actually wanted to ask you, but I gave you the answer, so let me skip the question. Makes it easy. So, as I told you, the second step is still O of t because we have it sorted, so we can just have a scan, O of t linear. But the first step now is O of t. I wrote something in gray, but it's O of t because all we need to do is process token by token every time we put it into the standard inverted index that we maintain, but we no longer need to sort anything. Because if you compute, you could tell me, yes, but we still need to insert the document ID and maintain it sorted. Yes, but if you process the documents in order and increase the document ID every time, that's actually only an append. You append the document ID at the end of the current posting list. If you use some B tree or some binary structure, you may have some logarithmic component in there, but actually you don't need to do range queries or anything there. So maybe if you use a hash table, it's good enough, and you still have O of t, right? Besides, it wouldn't even be log of t, it would be log of the number of documents in there, or the number of terms. So basically what we have here is that we have an actual complexity in O of t for this single pass in-memory indexing. So now we have two ways. We have the blocked sort-based indexing in O of t log t, but feels like O log O of t. And we have the single pass in-memory indexing in O of t, which scales up even better because we don't maintain anything, any state in memory. Who understood both BSBI and SPIMI? Not everybody. Who did not understand everything? Some of you? So do you have any specific questions on any part that wasn't clear in that? Okay, so if you don't have questions, here's what I recommend. And I really recommend that. I cannot emphasize it enough. There is chapter 4 called Index Construction. Everything, it's exactly what I'm doing here. Every week, we have one chapter of the book. So every time you don't understand something, read the book. You can do it at your own rhythm. The other thing you can do is look at the lecture. It's recorded. You can watch it again, right? If you don't understand anything, write to us. We are going to help you, right? And every week, I'm going to come back on the previous weeks. You will have exercises in order to do this as well, right? So do not hesitate to reach out to us if anything is unclear. There is a third way that I actually really like because of the fact that it's not just a single machine, but we can actually use clusters of machines, and this is now closer to what actual search engines are doing, is MapReduce. Who knows MapReduce? I think you saw it also in, do you actually use it in Introduction to Machine Learning? No, I think it's when you do it on large scale. It was in the large scale datasets lecture. So MapReduce is a way of doing what we've been doing, but spread over multiple machines. It's still the same idea that we manipulate tokens. So let me just use the last few minutes to tell you, for those of you who don't know MapReduce, with a very concrete example. The idea is very simple of MapReduce, is that here we have the collection of documents, could be anything else, but we shard it, and we have a query, and the output should be the standard inverted index, right? So MapReduce basically gives you a framework in an extremely simple way of structuring the query that you have into doing things in parallel, shuffling around, and reducing, which is again doing in parallel. Maybe here, you will already recognize what we've been doing with BSBI and SPIMI, because BSBI, the first phase, was actually doing stuff in parallel, right here, mapping. And then we shuffle around, it's basically when we merge everything at the end, right? So this may be reminding you of BSBI, but the big thing here is that we are going to use a different machine every time. We are doing it in parallel on several machines, not in sequence, right? So this is what MapReduce is actually about. So this is the whole architecture of MapReduce. Looks a bit complicated, but there's no better than a 101 that I actually did it with actual Pokemons in a lecture last year. Imagine you want to count Pokemons of different kinds. And I had, I think, 400 of them that I spread over the lecture room. And the end result that we want is this, right? We want to count the number of each. So the idea is that I asked 10 students, and I spread 40 Pokemons for each of them. What they did, they are called the mappers. What they did is that they counted the smaller quantity of Pokemons they had, and then they had this intermediate result here, the intermediate counts. This is exactly like in BSBI, when we only look at one shard of documents, and we compute the standard inverted index just for that one shard. This is one mapper. But this was done by 10 different people in parallel. And then we had reducers, 8 of them, because there was 8 kinds of Pokemons. And there was this phase in which the mappers cut their result with scissors. They only gave that part with the relevant Pokemon for a reducer. Each reducer was responsible for one Pokemon. And that part was actually a huge mess. This is the shuffle part of MapReduce. It took 5 minutes until everybody had given to everybody the tokens or the pairs that they needed. The shuffling phase is absolutely horrible in terms of complexity. And then what a reducer does, it's very simple. It just does the addition of all of this to a final result here. And then we got from the 8 reducers the output, and that was the final summary. Well, it may surprise you, but we are going to do exactly that, but with documents and tokens and building the standard inverted index, right? But this is something that we will do for next week. Now you have this overview of MapReduce, should be clear how it works. And that's the cliffhanger of now how do we use that in order to actually build our standard inverted index. So just before you go, as usual, please tell me your overall feeling. I can slow down, I can accelerate, depending on your level of understanding. That looks good. This is my favorite cell, 80 to 99%. Perfect. So I think that this is basically it for today. I cannot emphasize enough, please, I think the book is even online on the Stanford University webpage of the professor. Do not hesitate to actually go there, read the book. It is really complementary to what I'm teaching you, and it's exactly the same chapters and that I am doing. So I really recommend read the books. The exercises today, it will be on the building the K-gram indices for spell checking. Okay? So enjoy the exercises, enjoy your meal, and I'll see you in actually on the 13th of April. I think there is the Easter period, so I'll see you, I think, on the 13th of April. So enjoy your vacation, and see you then.